So excitement's definitely building with the SimpleX Super project. And here in part 4, you can see more parts are on the chassis. They're not all nailed down yet, but we're starting to get to the end. Decisions are being made, like what type of connectors do I want to use for the RF in, for the speaker. I prefer to use a BNC instead of the phono connector, but the phono connector is okay for the speaker. Those types of decisions. Also, you can see that we have a proper inlet and a fuse holder now. Just little decisions as you're building, and you will have a totally different build than this. You use the parts that you have, you use the components that fit on the chassis, and you make a lot of changes. The front's pretty much there from what you saw before. I have added a little control below the dial, and this is from a video I saw online where someone actually brought out the capacitor that's on the crystal filter. In other words, they brought the phasing control out. Not that they use it that much, but I put it right under the main tuning dial. I've got this big oversized knob on the main tuning dial I managed to find. Might be a little bit overkill, but of course, mechanical advantage, ease of tuning, big fat knob. The regen control ended up being way over here, and then over here is the regular control for your BFO. So I swapped places on those. Again, a decision I made as I was building. So other than that, it's pretty much what you saw before. We're going to take a deep dive into the crystal filter. Some of you are interested in how the crystal filter works. Best done on the bench with test equipment, not in the receiver. So let's see what this crystal filter is all about. Let's look at FT243, HC6 type crystals, and the HC49 crystals that I've got my hands on now. They finally came in. These are the $1 each crystals. I got 10 for like $4 or $5. So you can't beat that for the crystal filter. So here we are in part 4. Let's get started. So just a few practical issues. When you're working with the top of the chassis, getting ready to mark it and make some holes and mount some parts, basically I'm looking at the older SimpleX Super here. This is the Mark 1, and the newer one here. You'll see the older one has the shield cans on top. The older one has the unshielded coils underneath. And you can identify these coils pretty easily. This one's the mixer coil. This one here's the detector coil, and over here is the BFO coil. I like the location of the BFO coil because it puts it close to those two controls that I've got up front that I'm contemplating. One of them being the regeneration control, and the other one being the BFO. So they want to be close to this tube. Now my IF cans are a little bit bigger than the ones shown in this receiver, the Mark 1, but not a lot bigger. They look very similar, in fact. That's just by luck. I took them out of some piece of equipment that I parted out and got like 6 transformers out of it. They're not really transformers. They all were single-tuned inductors, so it was very easy to rewind them with Litz wire for the 2 megahertz band. So I can already see I've got things laid out wrong. This can doesn't really go here, or this tube doesn't go there. This can comes over, and this tube goes here. So that's more like what it's supposed to look like. Actually, they even put this up here. Now, I don't know if that's going to work out that way, but we'll see how this thing lays out underneath. I haven't committed to drilling any holes in the chassis. You can see this is where the power transformer is going to go. Here's the choke. I also have a Core-Com filter that'll mount on the back. That's where the line cord will come in. Pretty good layout. It's going to be fine. Kind of designing itself on top. It's just a logical layout. Basically, this thing goes right across the input to the output. The crystal filter is going to be in this area here underneath the chassis, probably on a terminal strip. So once you've got the front panel kind of figured out, and you can see I'm using some flathead screws here to attach the input preselector cap. Notice how I had to recess the phone jack because it just wasn't big enough to take a nut all the way through this and the inner box. Once you're done with this much work, now you can take the panel back off and you can start to work on the layout on the chassis itself. Starting to mount some parts on top of the chassis. Boy, that's an ugly hole, huh? Well, I don't have a machine shop, and I just use the tin snips, and it looks a little ugly. But you know what? Once I get the transformer on there, who cares? Looks great. And the same goes for the Corcom inlet on the back. Pretty darn ugly looking hole here. Inlet in. It's going to look fine. So with the addition of the crystal phasing control, the original bracket had to be discarded, and I had to make a stacked bracket that contains both the tuning and the crystal phasing control. I took this thing to show and tell night, and a lot of people were really enthused looking at the SimpleX Super. So let's take a look at how the top of the receiver came out after mounting the parts. The transformer and the choke look normal. Here we have the mixer tube. We have the mixer IF inductor. This single-tuned inductor, I went with the Mark I style with the shielded can inductors rather than putting them below chassis unshielded. Got the two cans a little close together, so I had to put the crystal filter in between the two coils. Then we have the detector tube, and finally the audio output tube. Here's the BFO coil. Everything looks fairly normal here on top of the chassis. Let's turn it over. Okay, on the bottom, you can see we have the regeneration control all the way to the left, the BFO. Then here is that new crystal phasing control. Of course, the main tuning below that. Here is the band select mode switch, the phone jack, and of course the mute switch. Looks like everything is wireable, and in the next video we'll start to get this thing wired up. There's a lot of considerations there. On the rear of the chassis, of course, we have the antenna terminal. I put a BNC in, a phono connector for the speaker, a fuse holder, and our IEC inlet. So everything is there. Okay, now for the boring, fun, crystal filter discussion. Of course, working with crystal bandpass filters, or filters of any type, is made much easier with a network analyzer or a SWEP generator and a scope. We can still do a lot with a simple generator going into a scope or some kind of detector to a meter. This is the method I will use to check out our simple filter. Before we begin our testing, let's talk about the simple crystal bandpass filter that's used in our receiver. This is really the most basic type of crystal filter, except for maybe the modern ladder filters that have become so popular in QRP rigs. A crystal represents a series inductance, capacitance, resistance circuit with its thickness, angle of cut, shape, and material determining the resonant frequency. A typical quartz crystal can have a Q between 10,000 and 100,000, compared with 150 to 300 for a high-quality conventional coil capacitor tuned circuit. A crystal used as a filter in a receiver is usually connected between two conventional tuned circuits at the input of the first IF stage. Such crystal filters, these simple single crystal filters, were used in the better receivers of the mid-1930s through the 1940s, and these single crystal filters were featured prominently in the military receivers of the day, including the BC-312, BC-342, 348, the RCA AR-88, the HRO, the BC-779 Super Pro series, and in the post-World War II Eddystones. Crystals behave as sharply tuned resonant circuits. In our filter, the crystal is series resonated at the intermediate frequency of 2 MHz. The crystal's peak voltage can be several times higher than that of the incoming signal. This is due to resonance amplification, or maybe a better term, resonance intensification. The response passband and steepness of the skirt achieved with such a simple circuit follows the crystal's resonance curve almost exactly. This means it's very narrow and misshapen, with a sharper response on one side than the other. It makes a pretty effective crystal filter, however, with perhaps 400 to 500 Hz of bandwidth to the 20 dB points, and a total rejection to adjacent channels of 40 dB. The crystal and holder, which we're going to call CX, are one element of a bridge circuit containing the three other capacitors. The trimmer acts as the phasing control so that the capacitance of CX is balanced out, and the undesired signals which are close and possibly interfering with us. So the phasing trimmer acts to null out the CX capacitance and consequently adjust the phase relations of the voltages and currents in the bridge. Now if that crystal is shorted out, as we see here by this switch, or perhaps a low-value resistance is switched across the crystal, the bridge becomes unbalanced and the crystal filter is effectively put out of circuit or bypassed. This is an effective way to handle wider signals like AM. When so shorted, the bridge becomes unbalanced and the crystal filter sometimes becomes lossy. Sometimes the signal will appear to drop in amplitude, and sometimes it actually goes higher depending on how they do the switch. After the switch is thrown, the amplitude change is normally made up for by changing your RF gain control, or in our case, the regeneration control in the detector stage. But does the SimpleX Super have a switch? No, but maybe we should look at that a little bit later. So how does the SimpleX Super handle AM at all, or even single sideband for that matter, with such a narrow filter? This is a great question. For single sideband, the voice channel is handled just barely by centering the filter in the middle of the sideband energy and by tuning the BFO appropriately. This lets the poor skirts of the simple filter leak enough energy to demodulate the voice signal. For AM, the BFO is turned off and the detector stage is put into full oscillation, which allows a single sideband form of AM synchronous demodulation to take place. It certainly will not be hi-fi AM, and we can explore that shorting switch idea once the receiver is wired and tested. Speaking of testing, let's start looking at crystals. So when we're checking crystals, and I've got a little fixture here that simply puts the crystal in series with a 50 ohm line. I've got 10 dB on the input, 10 dB on the output, just to have, impedances that we recognize on both sides of the crystal. Now when we have a system like this, and we're looking for series resonance, okay, we can tell the resonant frequency because we'll have a maximum output on the series resonance. We'll be able to measure that frequency on a meter. We'll also be able to measure the relative series resistance of the crystal, which indicates what kind of loss we're going to have in our filter and how sharp the filter is going to be. So my little $1 crystals showed up, and these crystals says that they're loaded with 18 picofarads to be on frequency. This simple setup could be done with just some test leads, but I formalized it by putting a 10 dB attenuator on one side and a 10 dB attenuator on the other side in the form of this adjustable one. It's what I had, so I just pulled it out real quick. So we have the crystal literally in series down this line. All you do is you go to the scope and you peak the output, and then you look at the counter, and there you are. Okay, so that tells you the thing is 50 hertz off with its 18 picofarad loading. This is a good crystal. Okay, all we're measuring is the series resonance of the crystal. So next I've got a 2 megahertz FT243 crystal that I happen to have that came off an old generator. They were using this as a calibration crystal. Similarly, I resonated it. This guy's coming out a half a kilohertz low. We could take the HC49 and put it in an FT243 holder and then have a socket and make it look cool. You have function, and then you have vanity, and that falls under the vanity. We want to have something that looks like it came from the early 60s, so we take our little crystal that we know is funny looking and doesn't belong in this project, and we put it inside the holder and fake everybody out. But this is a relative measurement. So let's look at the scope. Looking at the scope, I'm just going to peek that up. Okay, see where that is? Now we're going to change this FT243 to our new crystal, the HC49. There's no cap in series now. Okay, now we have the HC49. I'm just going to peek it up on the scope. Ah, what do you notice? You notice that the amplitude's much higher. That means that this HC49 crystal has a lower series resistance than the FT243 crystal. Now the FT243 could be dirty, it's old, we might be able to clean it up with some alcohol, but you can see this has a lower ESR, and we would expect this to possibly have a sharper response and lower loss than the FT243. Let's try an HC6 crystal. Okay, here's the HC6 crystal. This one's 2001 kilohertz. On the meter it's resonating at 2848, and it's off the scale. This is the clear winner. This HC6 sealed crystal is beating both the FT243 and the HC49 for series resistance. I went as far as to build the filter. Yes, I built the filter outboard just so we could look at it with our HC49 crystal. Now the method I'm using to tell what the bandwidth of the filter is interesting, but let's go through the circuit first. We have the coil and a 100 picofarad capacitor, the two 200 picofarad capacitors that are center tapped with the middle grounded, the crystal, the trimmer, and then a 5 picofarad going to the load. And for the load, I'm using a 10K resistor and a 1K resistor because I want to investigate what the termination does to the filter. To couple into the filter, I'm using a 3-turn link, which I've added to L1. And off that 3 turns, we have the 50 ohm drive out of the generator. And I'm using an attenuator. This attenuator is going to be helpful because it is going to simulate how much loss I have in the filter to represent the filter shape. So for instance, if I have the filter out and I'm looking at the scope, let me get up to the scope, and I tune the filter for resonance, okay? As soon as the filter shape goes down by 10 dB, I'm going to flick in 10 dB. Here we go. That's 10 dB with my attenuator. As soon as we tune the filter, and it looks like that on each end, we know we have the 10 dB points. Let me take it out. Let's start tuning. Okay, that's approximately right. So now we look at the meter and we see that it's 969, just below 2. Tune the other side, we'll go down in frequency now. Through resonance, down in frequency. And let's see what it says, it's 645. So I think you could agree that we're looking at a 380-ish hertz filter, just about 400 hertz filter. That's what we got out of the box. Now I've peaked it both with the coil and with the trimmer in the middle, and we ended up with basically a 400 hertz filter to the 10 dB points. That would make a pretty good CW filter. You're definitely going to get single signal performance out of that. I don't know how good it'll be with sideband. The next trick, I'm going to put another crystal in parallel with the first crystal. Okay, I've now got 2 crystals in parallel. I need to maximize things. Got to get on frequency first. Okay, oh yeah, I noticed that all of a sudden we've got more output. So that's one effect. 2 crystals, less series resistance, right? So let's bring that down a little bit and peak everything. Okay, let's go for the high frequency first. Okay, there's the high frequency. 2,100 above, okay, 100 hertz above 2,000. And 669, 700, that's, so what are we talking about? 100 above, 600, 400, 370. It's about 100 hertz we've added, so we're closer to 450 now instead of 370. So it has broadened it up by using 2 crystals. And it's lowered the loss. We have less loss, and we have widened the crystal filter by using 2 in parallel. Part 4 got a little bit long, and really we only have one more place to go with our project. With pretty much everything mounted on top, all of the action goes below ground. We begin to think about wiring this thing. Now, one hint on part 5, which will be the wiring of the radio. With a receiver, you always start at the end and work back toward the antenna. So the first thing we'll be working on is the power supply. Then we will work on the audio amplifier speaker driver. Then we will work back to the IF. And finally, the front end and the preselector coils. So with a receiver, you always work backwards. And with a transmitter, you always work forward. You start with the crystal oscillator or the VFO, and you work toward the antenna. Stand by. We need to wire the SimpleX Super.